This is going to be the fourth and the last lecture on instanton mechanics for single particles in a potential. After this, we'll go on to field theory. So just to recall our agenda, we've done the path integral, imaginary time, instantons in a symmetric double well potential, and today we'll talk about metastable states. But before we do that, I want to give you some basic reminders from quantum mechanics. H is a Hermitian operator if it's equal to its Hermitian conjugate. Its eigenvalues can be easily shown to be real, and states preserve their norm in time as you evolve them forward. Well, let's check this. So here is the evolution operator. Remember that this H here is time independent. And so this evolution operator takes the state psi of 0 into the state psi t. And so if you compute the norm of the state psi of t, then of course you have this. So in the complex conjugation, we get H dagger, H Hermitian conjugate, and I goes to minus I, and so of course you have this, and if H dagger is equal to H, well then the norm is constant, it's preserved. Okay, but where we are going to be interested in today is in Hamiltonians like this. This is a single particle kinetic energy, and even this can fail to be Hermitian. Normally, when one is teaching quantum mechanics, one always says, oh, this here is a Hermitian operator, but it's not always true. So let's take H dagger between psi and psi. That's, of course, p squared psi conjugate with psi. I haven't shown psi of x, but that's obvious. And that's, well, the Hamiltonian is minus h bar squared over 2m into the second derivative, in this case acting on psi star, psi. All right, so then the next step is just do a simple differentiation over here to see that this is actually exactly equal to what's below over here. So there's a d by dx of this. I mean, we can do this mentally because d by dx of this is d2 psi star by dx squared, and then there's psi, and then d psi star dx, d psi by dx. That cancels here with d psi star by dx, d psi dx, and then there's an extra term left over, so that extra term is put over here. Okay, now here one uses the fundamental theorem of calculus that d by dx of this is evaluated at the boundary points from here to here, and if it vanishes over there, then of course only this term will be left over, and if this is 0 for whatever reason, it could be because psi is 0, or it could be because psi is real. If psi is real, then this term over here, which you will recognize as the current, well, that current is not leaking out at infinity. So that's 0, which means that this thing just becomes p squared over 2m, and that's, of course, equal to the norm, that's equal to h psi with psi. And that's exactly what one means by a Hermitian operator. Hermiticity has been confirmed, but this, as I said, is true only if there are no boundary terms. I mean, that all the boundary terms vanish. In other words, there's no current which is leaking away. Now, if there is current leaking away, then H is not equal to its Hermitian conjugate, which means that the eigenvalues of H will have an imaginary part. So then the energy will have a real part and it'll have an imaginary part. And so if you stick this over here, then you'll get psi of 0 times the real part over here and this is the oscillating part. It remains, the magnitude of this will remain constant in time. But now there is also this e to the minus gamma times time. And this is a decaying state. So, for example, there could be an atom which decays, has a lifetime, and this gamma is related to its lifetime, or rather, 1 over its lifetime. Okay, so now we come back to particle tunneling, and we'll talk about the decay of a metastable state. Now, this over here is a potential. It's a stable vacuum. It'll have real eigenvalues. You can see that there is no way that, this is just solving the Schrodinger equation with this potential would give you a bunch of real eigenvalues. And for this as well, again, in classical terms, this would be a stable vacuum. So if you started off with a particle over here, it would tunnel across to here and tunnel back and forth. In this case, it would tunnel down to here, but then it could also, in principle, come back over here for a while. But you see, the point is that this potential is rising over here, rising over there, and so the particle is confined between the wall here and the wall here. But here is a metastable vacuum, and in this case, what will happen is, if you have a particle, if you start with a particle over here, it'll tunnel across to maybe this vacuum here. It's not it is a kind of vacuum. I mean, it's pretty flat, but it's still a vacuum. But then out of here, it'll tunnel down to this side. And so probability will be lost, which means that this will be a decaying state, and the eigenenergies of the Schrodinger equation will be complex. Okay, so now let's look at the decay in a closer way. Here's our potential, and here's our particle. The particle will be assumed to have zero energy. This is an unstable part. It's an unstable vacuum because it can tunnel across and be lost. We will call the second derivative of the potential at this point V double prime. And that'll be the same. Well, it should be V double prime at 0, actually. So that's a mistake I'll correct later. Here is minus V of x. Here you see that the particle starts off on the hill and it goes across. Now we're talking of instantons. The instanton will go from 0 to A and back. Let's do a few definitions now. This instanton will travel from the origin to the point A. You see, it's actually doing a tunneling. So from here to here. But see, when you invert the potential, it looks like a particle which is sliding down a potential and going up. Okay, so just keep this in mind that it goes from 0 to A. It starts out from here at time minus t by 2, as we did before. It arrives at this point A at time tau equal to 0. And it then goes back to 0 at time t equal to tau, at time tau equal to t by 2. Remember that at the end, we're going to take this t to go to infinity. Now, the bounce, so this is what Coleman called the bounce. It goes from, the instanton goes from here to here, bounces back. And that's the bounce solution to the equations of motion. It happens very fast, and most of the time is spent in the transit. Very little time is spent here at the point A. And let's see why. Now, this is going to be very important because we're going to make the dilute instanton approximation, and we're going to allow the instantons to go and arrive here at time t by 2, at time tau equal to 0. But where is the 0 to be located? It can be located anywhere. Then that's because of time translational invariance. And so when we come to summing over all different instantons, we will be using time reversal invariance once again. Okay, so here is tau equal to 0. The bounce, so this is x when it's here at x equal to a, tau equal to 0. Remember that the energy is always conserved. And we started out with 0 energy here, and there's 0 energy here as well. So this thing must always be equal to 0, which means that xb dot, and this means dxb by d tau at x equal to a, that's 0. It stopped over there. Okay. But look at the equation of motion. The Newton's law for the instanton. And remember how we got the Newton's law for the instanton? We expanded the action, and then we said that the first order in action has to vanish. When it vanishes, the condition for it to be 0 is that xb double dot is equal to this. Now look over here, v prime at a. So here you see that the slope is highly negative, which means that xb double dot is highly negative, which means that it's accelerating towards 0. And the bigger this is, v prime, the faster it'll go. So if we make let's just differentiate this over here, xb dot, we haven't specified a v, this is general, but we can get the general outlines of the solution. So if you differentiate xb of tau, then this is what it'll look like. At this point here, the derivative is 0, and that's why xb dot is 0 over here. And then further away, it'll also become 0, but here the derivative is increasing, and so it's increasing and then decreasing, and then this is the general graph for xb dot. Okay, now to remind you how we expanded the action in lecture 2, there was the classical action and there was the fluctuation action. So the classical is this, and here it's the kinetic energy plus the potential energy. So remember that this is not the conserved quantity. The conserved quantity is minus over here. So this is the classical action. And then, just to remind you, we start out at 0. We go on a path in configuration space. We arrive at A, So this is the other end, and then we make our way back to 0. Now, there is also, so this over here, it just reiterates that xb at minus t over 2 is the same as xb at plus t over 2, and xb at 0 is a. So this is 0 and that's a. We start at minus t over 2, end at time plus t over 2, and at time t equal to 0, we're at the point A. There's also the fluctuation part. So all kinds of fluctuations that the Feynman path integral says we have to sum over. Now, let's take this and expand around the point x equals a. That's pretty trivial. xb dot is 2 times square root of v of xb. When you expand that around the point x equals a, then of course the first term over here will be the derivative into xb minus a. Now, here's an interesting point. This bounce velocity, so xb dot, it's a solution of the equations of motion, but it must be an eigenfunction of the operator over here with 0 eigenvalue. And so this is just like in the previous case that we did with the symmetric well. So far, we are not doing anything different. I'm merely reiterating what we had done in lecture 2, basically. So anyway, this is pretty easy. If I take this operator, I apply it on dx b by d tau, then because d by d tau commutes with d2 by d tau squared, you get d by d tau of this, and then the equation of motion says that this is equal to 0. Hence, this thing dxb by d tau is an eigenfunction of this operator with 0 eigenvalue. And of course, this obeys the correct boundary conditions, which you've now seen many times over. So the instanton, the bounce instanton, is at rest to begin with. It's at rest when it comes to the point A, and then when it goes back to the point 0 at time t over 2, it is at rest over there again. Okay, so far there's hardly any difference from what I did earlier. In fact, there's no difference. But now there's going to be a very crucial difference, and that's going to make all the difference. So you see, xb dot of tau has a 0 eigenvalue, but it has to have a node. A node is where a function is 0. So you see that here's a plot of xb dot. If xb is this, as I said earlier, if you differentiate it, it's got to be 0 over here. Now, we know from our experience with the Schrodinger equation that if you have an eigenfunction that has wiggles in it, that means it's got more kinetic energy. So, in other words, more nodes in xb means more kinetic energy. xb dot squared is bigger. See, it's even the sign doesn't matter. It's xb dot squared, and hence there's more kinetic energy. And so that means that there has to be a node which is below the 0 mode. In other words, you've got to have a negative lambda. Okay, now this is going to create a big problem, because earlier on, you see, when, for example, we took the harmonic oscillator, we said, oh, let's calculate all the eigenvalues of this operator over here and all the eigenfunctions, and then we can do the fluctuations for the path integral by expanding in a series. Xb is equal, x equals x classical plus Cn phi n, and sum over n going from 1 to infinity. Okay. Then when you do that, you have to do this Gaussian integral. This Gaussian integral over here gives you 1 over lambda n square root, and that's the determinant of this operator over here, which is fine. Everything is okay. But now, as we saw in the case of the symmetric double well, we had lambda 0 is equal to 0, but that was the last mode. Now there's a mode which is negative, which means we have to do this integral over here with lambda minus 1, which is negative. And so we have something like this. We have to do an integral over c e to a positive number c squared, and that doesn't seem to make any sense. So is it possible to make sense out of nonsense? I mean, this is badly infinite. It's not only infinite, it's badly infinite. Earlier on, it was quite bad because we had lambda equal to 0 over here. So then we argued around and said that that's an integral which is proportional to time. It turned out it wasn't quite so simple. There was a factor in front, and so we had to argue for getting the right measure. But here, it seems terrible. So here is a situation where we must understand the physics very well. Again, for your viewing pleasure, here's the potential, negative of the potential. And now I'm going to ask you to look at the space of all paths which satisfy the boundary conditions which I've repeated very often. And I'm going to say that let C be the value of x at tau equal to 0. Think of it this way, that there's an instanton which started from here, rolled down, and maybe arrived over here, and this was the maximum that it could go to at time t equal to 0, and then it rolled back. So C is going to be a parameterization of the maximum value of x which is achieved, and that is at tau equal to 0. Okay, so I'll draw this. Some paths will undershoot. That is to say, they will not reach A. So some path will reach here. Other paths will reach here, beyond A. There's only one path which will arrive at A, and we know that that is the path which is determined by the principle of least action. In other words, for which S prime at A is equal to 0. Okay, so we will associate a definite value of action with each value of C. So undershoot, these do not maximize the action. These do not minimize the action. These do not minimize the action. The action is, now I used a bad word. I shouldn't have said minimize. Extremize, I should have said. The action is extremized only at C equal to A. So the path which just reaches A is the one that extremizes the action. And that's really the condition that the first functional derivative vanishes. Okay, so Now, to give meaning to the integral over c minus 1. So you see, we have to integrate over all the c's. We have to integrate over dc minus 1. And here we shall have to use analytic continuation. But before we get into the mathematics, I want to tell you what I said at the very beginning, that certain operators are Hermitian if there's no loss of probability. But here is something that is going to disappear once it reaches A. Then it'll scoot down all the way over here. And so we expect that there will be an imaginary part to the eigenvalues. Okay. And if there's an imaginary part to the eigenvalues, then we will have an imaginary part in the probability amplitude. So this is speaking in general physical terms. Okay, since some of us are a little rusty on complex variables, others are up to speed, but let's just quickly go over the theory of complex variables. So take a function which has a real part and an imaginary part. The real part is a function of z. But what is z? Z is two variables, the real part of z and the imaginary part of z, one which we call x, the other which we call y. So actually we have f is a function of x and y. The real part is a function of x and y, so is the imaginary part. Now, we learned in basic complex analysis that if a function is to be differentiable, if a complex function is to be differentiable, then it shouldn't matter whether you approach it from the x-axis, from the y-axis, or anywhere in between. And the way to get the same answer is that the Cauchy-Riemann equations have to be satisfied, which are that du by dx is dv by dy, and dv by dx is minus du by dy. That, if it holds, you say that the function is differentiable at that point. Okay, now if the Cauchy-Riemann condition holds, then all you have to do is, okay, so let's do it mentally. Differentiate this side with respect to x, so you get d2u dx squared. On this side, you get dv by dxy. Now, you differentiate this by y, and that gives you minus d2u by dy squared. Add them, and this is what is called the Laplace equation in 2 dimensions. So you have the Laplace equation in 2 dimensions, both for the real and for the imaginary parts. Okay, now suppose there's a function which has an extreme point. So its derivative at that point in the complex plane is 0. And of course, if the derivative is 0, that means the real part and the imaginary part, whether differentiated with respect to x or y, must be 0. So all first derivatives are 0, in which case this will be an extreme point. I'm not saying it's a maximum or a minimum. It's going to be an extreme point. In fact, it can be a maximum or a minimum, and it can be worse than that. Now, if the second derivative is negative, you see from the Laplace equation, then that d2u by dy squared must be positive. This is negative, this is positive. If this is positive, this is negative. And so we have a situation where the real part's second derivative is one sign, and the imaginary part's second derivative is the other sign, which means that we are at a saddle point. And This actually, we'll picturize it later, but you see that from this condition, the Cauchy-Riemann condition, that we get, just check this out, it's pretty trivial, du by dx, dv by dy, and similarly over here, that this is the gradient of u dot the gradient of v being 0. Now, when two vectors have 0 dot product, that means that they are orthogonal to each other, which means that if we call one the phase, the other will be orthogonal to it. And so contours of constant phase, and they're also contours of steepest ascent or steepest descent. Now, just to give you a picture of this, here's an absolute maximum, actually two maxima, and here is the saddle point. And now, because I'm going to use the saddle point a lot, I'm going to take Mathematica and ask it to make me this surface over here. And you see, it does a very good job. And if and this makes it very clear that if I go on this path, if I go on this path, A, Z naught, B. Now, at this point, Z naught, I have an extremum. So here I have a minimum on this path, but if I go on the path C, Z naught, D, there's a mistake over here, this should be D, I'll change that in the notes, then on this path, it's a maximum. So a minimum on one path, a maximum on the other path. Okay? We have to now do a little more complex variables. Suppose f is differentiable in a region, then it's called analytic over there. And then Cauchy's integral theorem says that if you integrate on any contour that surrounds that region and there are no singularities inside, so no poles, no branch cuts, no nonsense inside, then this integral is equal to 0. And it will be 0 for every gamma, every curve, provided that f is analytic inside that region. So this means that I am allowed to deform the integration path as long as I do not cross any singularities and do not go over a branch cut or anything like that. Okay, so we're interested in calculating an integral like this, as I said before, with lambda negative. Right? So then what we will do is, we will go to the complex plane and we'll deform the integration path as we want, provided we obey the rules. That is to say, we avoid all singularities, such as poles, branch cuts, essential singularities, whatever. And so let's consider a general integral of this thing, of this type, with epsilon being small. Now you see, the reason I've taken this integral is because we are taking h bar to be small, and we're going to let h bar goes to 0. So here I'm going to let epsilon go to 0. And this is an analytic function, assumed to be analytic everywhere. That will be, of course, the action. The action is smooth, analytic. We don't have to worry about that. All right, so in that case, I'm allowed to always expand my function f of f in terms of the first derivative. There's no second, in terms of zeroth derivative. There's no first derivative because f prime at z0 is equal to 0. And then there's the second order term, and let's then look at this integral from a to b. And here's our integral. I've just going to stick this in here. So the first term being a constant, I can pull it out of the integral. The second is this. Nothing very much except just put this over here. Okay, now here I'm going to change my coordinates. I am in the complex plane, so my integral was along the x-axis, purely real, but now I'm going into the complex plane and I'm going to change coordinates. Z minus Z naught is equal to the real part of this thing, and there's e to the I theta. Okay, I'll stick that in. Well, dz is equal to dr, e to the I theta. Now here theta is something that I am going to fix according to my own convenience, according to my own liking. This is not a variable of integration. This is something that I choose. So dz is equal to dr, e to the I theta, and there's only the integration over r. And so there's the exponential, f double prime. Z minus Z naught squared is r squared e to the 2 I theta, because that's multiplying two of these together. Now, we will be interested in the case where this is negative. F double prime at Z naught is negative. So I'm just going to write this as minus its absolute value, stick that in, and of course this makes it look just a little bit different, nothing else. Now here I have still the choice of theta to make. What choice should I take for theta? And I'm going to take theta equal to pi by 2 for the path of steepest descent. Well, steepest descent or steepest ascent, depending on whether you're going one way or the other way. If I do that, then this, see, the important thing is, if I take theta equal to pi by 2, this becomes over here minus, which means I'm going to get a minus over here, which means I'm going to get a convergent integral. And you see over here, theta equal to pi by 2, stick it in here, e to the I pi by 2, everyone knows that's I, imaginary iota. And now you see that we're getting to the imaginary value, as we should on physical grounds. The state is decaying. Okay, so out comes the I. We have to do this integral. Now here you see, how did I change the limits of integration from 0 to infinity? That's because in the limit that epsilon goes to 0, the only thing that will matter is small values of r. So this upper limit over here could be something else, but it doesn't matter, because if epsilon is small enough, then the rest is exponentially small. So this is called the method of steepest descents, I think invented by Laplace 200 years ago. And so anyone can do this integral. It's you remember if it was minus infinity to plus infinity, I'd get a square root of pi over the stuff over here. But since we're doing only half the integral, there's half coming out here. The important thing is that there's I over here and there's a half over here. And now this, well, I took an integral like this, but the real integral is pretty clear that we're looking for the integral with the negative eigenvalue. And so this f of z0 is just the action for the bounce, and this f double prime is just lambda minus 1. Okay, and so we are pretty much done, and we're going to move towards the final result. If you include the fluctuations and you integrate over all bounce times between minus t over 2 and plus t over 2, and you assume that there's just a single bounce, so the instanton has gone from 0 to A and come back in time t, then the amplitude for this single instanton to go from here to here, then you must integrate over all paths, which we have. We've integrated. So at the level of order 2, we have done a complete job. It's the normalization constant. This was just the classical, so you remember e to the minus f prime at z0. That's what this is. And this h bar is your epsilon. This stuff over here, you will remember from the last lecture, is just the time translational stuff. So if you since the bounce could happen any time between minus t over 2 and plus t over 2, that means we have to integrate over all times, and that gives the factor of t. And this is, of course, the thing that we did last time, the measure, which comes out right. I over 2, you just saw how that comes through. And now here, this prime I have put to say that we must exclude the 0 eigenvalue and the minus eigenvalue. We argued that there is a there's a minus negative eigenvalue. Okay, so then what we had earlier then goes through pretty much as before. The only difference is this factor of half, because we did half the integral from minus infinity to plus infinity. The rest is as it was before. So what is this? And this stuff over here? Well, we normalize with the simple harmonic oscillator, and that's why this simple harmonic oscillator, you remember the simple harmonic oscillator is V equals half omega squared x squared. We always take m equal to 1. And so if you differentiate it twice, you get the second derivative as being omega squared. Okay, so everything is exactly the same as before. Here is the single instanton amplitude. And in the limit where t becomes very large, we saw that this thing over here, we saw this in the last lecture, lecture 3, that this goes into this. Now look over here, there's iota I, which we got because we went off into the imaginary plane. The rest is as before with this definition of k now. So there's a half as well. And now if we want to take all instantons, that is to say all bounces. So you see the first instanton can go at time minus t over 2 and arrive at time tau equal to 0 and then return at time plus t over 2. But then I can always shift all the times back or forward. There's time translational invariance. The only thing that I have to respect is that the second bounce happens after the first bounce, the third bounce happens after the second bounce, and so forth. But now, unlike the previous case, I can sum over. I don't have to worry about summing over odd numbers or even numbers, because I just want my instanton back at the starting point. So 1 instanton, 2 instantons, 3 instantons, I will just sum over all of them. And now this sum is so easy to do because it's just something to the power n over n factorial, which means it's an exponential. And so we get our final result back over here, exponential of this. That's pretty much it. Of course, there's an assumption over here that the bounces happen very, very quickly, that one bounce doesn't, that the second bounce and the first bounce are separated by some decent amount of time. And barring that, you can take any number of instantons, and so just sum from 0 to infinity, we get this. All right, so now we are at the end, or very close to the end, and let me just put the final touches. So we're going from position 0 back to position 0, evolving through this e to the minus ht over h bar, and we're going to stick this operator in here. And when we do that, then of course you're going to get two wave functions, something times its conjugate at the point 0. Both of them are at the same point, 0. So H will act on the first eigenstate and give you the lowest energy, and then there'll be this next lowest and the next lowest. And now when I make t go to a very large number, then this will become much smaller as compared to this. And so if I take the log of this, well, there's only this one term left. The log of this will be the log of this plus the log of this. And when t is large enough, then this is the only thing that will matter. So log of z will go to this. Okay. So now, from the previous slide, where we had z was equal to this, let me take the large T limit over here. If I take the large T limit, then obviously I'm going to get e to the I t. Well, it's there before you. So log of z of t then has a real part and an imaginary part. Okay, but now we are pretty much done, because look over here, minus E naught t over h bar, and here there's the same thing, and we've therefore found that the ground state energy eigenvalue is the harmonic oscillator eigenvalue, but there is an imaginary part to that because now it's decaying. And how much is the decay? Well, that's this thing over here. And this is a highly non-trivial result, because this is extremely non-perturbative. You see there's an h bar over here, there's a finite action over here, and there's a k over here, and that k is, well, we'll just come back to that. The most important thing over here is, of course, what is SB? SB is equal to this thing, as we saw much earlier. So we're integrating from the starting time to the ending time of this action, of this Lagrangian in imaginary time? Well, we know that energy is conserved. So V of xb is equal to half of xb dot squared, which means that we just have one term over here, and now some minor simplification which we'll carry out. So I'm going to take d tau, divide by dx, and then there's dx, and we go from 0 to a, but we also go from a to 0. So there's a factor of 2 over here, and so we are here. That's SB, the action for a single bounce. Single bounce action is determined entirely by the potential that we are considering. And so this is my last slide. It's the great grand result, which says that we have succeeded in calculating the decay amplitude, gamma. It has this form, there's something times e to the minus b. And this is well, you can just look at the dimensions. This is probability per unit time for tunneling out of the unstable vacuum. So the probability that this particle over here will eventually disappear by going over the hill. And so this could be an alpha particle escaping a nucleus. It could be the, well, yes, at the moment that's all we can say. But then later on, this could be the universe escaping its original state. But what is the result? A is this thing. It's not simple. SB is simple. This action here is simple. We've calculated that SB is this thing, 2, 0 to a dx square root of it. But of course, there are these determinants to be calculated, and you can't calculate them unless there is a specific V that you have given to you. But assuming that you have, and assuming you're clever enough, then this determinant over here can be calculated. That's now then a matter of detail. What we have is this as our grand result. Okay, some more references. Most of them are the same as last time. But this is a very good book by Ashok Das. Have a look at that. I think that this book here is quite complete, but it's also quite dense. And so I've tried to make sense of it in my own way. Right, so we're done.
The slide where we had the problem in our integral, the Gaussian integral.
Let's see.
Yes.
Yeah.
So without going into the physical interpretation, can we just stick an iota here, and we know that the integral would make sense? Then we can interpret its physics.
No, you cannot do that, because this is a very distinct instruction that you have to integrate from minus infinity to plus infinity. This actually came from the orthonormality of the eigenfunctions, and that is something that you have to respect. Okay, you cannot say that, oh, just because I don't like infinite integrals, I won't consider them, because then you'll get a wrong answer.
Actually, what I said was we just consider iota lambda into c square in the exponential. So the integral from minus infinity to plus infinity with an iota in the exponential, I think that has a finite answer. Just iota in the...
Whether it's finite or not, there's no legitimacy for that. There's no reason for you to do that. It's, see, what the guiding principle is, don't change the integral, but change the integration path.
Yes.
You are allowed to do that. You're not allowed to change the integral.
Okay. All right. So another question I had was from the slide where we kept our theta to be pi by 2 for the steepest
Okay,
descent.
I'm glad you asked that. Okay, let's go to that. So um, we were actually going along this path. C like this reached over here. So just as you reach the top, you are then at the point where the action has been extremized. Okay. Now, if you keep going, on this path, okay, just a minute, I have to get this cursor back. If you keep going on this path, then you're going to go down, down, down. On the other hand, I know that I can change my path of integration by going up in this way. So I'm going to change my path by 90 degrees and go, instead of going down, I'm going to go up. But when I go up, I get the iota.
That's why we have kept theta is equal to pi by 2.
Yes.
Okay.
Yes.
Can we describe this vacuum decay or maybe relate it to the decay of a particle? Because usually we say that we need quantum field theory to describe decay of particle. We cannot explain it in quantum mechanics.
So, okay. So why does, let's say, a neutron decay? You could ask that question. Well, how would you calculate the rate for neutron decay? That involves very different physics from single particle quantum mechanics. There, you would have two quarks exchanging a W or a Z0, and you would have you would have a quark, a U quark, being changed into a D quark, or D quark being changed into a U quark. And so behind that is quantum field theory, and behind that is the QCD, is the electroweak Lagrangian. So that is not a tunneling process. That's a scattering process. Here we are talking only of tunneling processes.
We talked about the nodes in our wave function, and that led to a negative index of lambda, right?
So we established that there was a zero eigenvalue and that it had no nodes, but there is one below, because there is XB has a node. Now, because it has a node, it will have higher energy.
So there is still something below it.
Yes.
Yes. And then how can you say there is just one mode below it, just -1? Why not -2? And if we consider more nodes, I mean, one below the axis 2 and 3, would there be more negative indexes with lambda?
That's a good question. Why is there only one negative eigenvalue? I would have to think about that. Having one below that and below that has to do something with eigenvalues being bounded from below. There's some kind of a theorem which is not coming to my mind right now. But yes, that's a good question to ask. Let me think about it. Okay, so then we're done.